And the next speaker is also the last speaker. It's Sofia Tromboni from Politecnico di Milano.
Yes.
I just... Could you... Is it
Yeah,
on?
the PowerPoint one is good. Yeah. Thanks.
Please.
Okay. Good morning, everyone. My name is Sofia Trombini. I'm a PhD researcher at Politecnico di Milano under the supervision of Professor Lorenzo Fagiano. And today I want to present you the results of the first part of my PhD dealing with the Kite-Platform interaction in offshore airborne wind energy systems. So today we will see this first part of my PhD. So we will have a little bit of introduction with the model that we use for the offshore airborne wind energy system, and then the study of the Kite-Platform interaction. But just to have a general overview of what we want to do, the idea is also then to focus on control and optimization of this system in the offshore environment and to estimate the power production in an offshore airborne wind energy farm. So this is the conceptual and general layout of an offshore airborne wind energy system in which we can identify two main subsystems. The first one, the airborne wind energy one, while the one that stays in water, which is the platform subsystem. Starting from airborne wind energy system, we decided to use soft kites. So the two main components are the soft kite and the tether, which connects the kite to the platform. And as a model, we employed a point mass model in which we have three main variables describing the position of the kite, which are the two angles of orientation and elevation, and r, which is the distance of the kite from the reference frame. Using and combining these three variables, we are able to define the equations of motion of the kite, which are the ones that we can see in the green box. And concerning the tether, we modeled it as a spring, a simple spring. So the traction force, depending if there is traction or if the tether is sagging, is zero, or is simply the elongation of the tether multiplied by the spring constant. Moving then to the platform subsystem, the two main components are the platform and the mooring lines. So we employed a simple cylindrical spar for the platform, which has a diameter of 10 meters and also a height of 10 meters. And for the mooring lines, we have 4 catenary mooring lines, which are symmetric with respect to the platform itself. The model, the idea of the model is similar to the one of the kite. So we have a vector v containing the variables that we need to describe the position of the platform, which are the displacement along the three axes x, epsilon, and z, and the rotation along these three axes. While on the left-hand part of the equation, on the right-hand part of the equation of motion, we have the forces. The first two, the Fh and Fr, are hydrostatic force and moment, and the radiation force and moment, which are like the forces and moment related to the hydrodynamics of the platform. And then we have the excitation force that I will detail more later, which is the force of the wave, the traction force, so the force of that the tether applies on the platform, and then the mooring force and moment, which is the force due to the mooring lines. In particular, we modeled the mooring lines as a mass spring damper system. So as you can see, the mooring line force is that one. So moving to the wave model, we employed the Jones-Webb spectrum, which is a model used in hydrodynamics to model the waves. And it is a spectrum defined by three main parameters: the peak wave period, the significant wave height, and the peak shape parameter. Defining different values for these three parameters, we are able to define different waves, much more intense or less intense. For our simulations, I don't know why this is not correct, okay? But for our simulation, we decided to take two types of waves. The first one has 3.7 as a wave period, 0.5 meters as a significant wave height, and 3.1 as peak shape parameter, and it is like a calm state of sea. While for wave B, we increased a little bit the parameters, both in terms of period and significant wave height, in order to have a state of the sea which is a little bit more agitated, more intense. So combining the equations that we have seen before, we can derive the overall model. And in this case, we have the variables, which are the one that we have defined before, both for the kite and for the platform. And then we have the forces, one for the airborne wind energy system part, which is the wind, and the other one on the platform, which is the excitation of the waves. Just a little talk about the flight control system that we use, because we will need it later for the study of the interaction. So we employed a control system focused on the use of two targets, which are symmetric to a central direction, and changing the angle phi, which is the velocity angle, we are able to define this A-path shape, changing from one active target point to the other target point, depending on the position of the kite. So I just want to move now to the kite-platform interaction, which is the focus of this study. So it's quite important to understand how the kite influences the motion of the platform and how the motion of the platform influences the operation of the kite, just in order to understand if there is a feasibility of the cooperation of these two systems, and in particular if we have interactions and too high motion, we can have problems with loads and possible damages of the structure. So we decided at first to study the frequency and the resonances of the platform itself in combination with the frequency of the flight, which are also the frequencies of the tether force. And in this graph, you can see, for example, the resonance and the force for the z direction. And as you can see, there is apparently no interaction. But if we move to the x and epsilon direction, we can see that peaks are much more near. And in particular, for the epsilon direction, we have like an overlapping of the two peaks at a frequency of 0.0185 hertz. And as I said before, this is a problem because this increases the motion of the platform. This complicates the operation of the kite and can lead to damages in the structure for increasing loads. So we want to go a little bit more in deep inside this interaction, defining a new parameter, which is the ratio of peak of the sway oscillation and peak of tether force component along the axis, epsilon axis, and studying this parameter depending on the length of the tether, we can see that this parameter increases till a frequency which is equal to the one that we have seen before, a frequency of flight, which is 0.0185, and then the parameter starts decreasing again. So, like, we proved that if there is this interaction between the resonance and the tether force frequency, and so this can be a problem for the operation of the system. So, moving to the control, so how we can mitigate this effect, how can we avoid this overlap between frequencies. The idea is to change this flight that you can see in the plot, so not to fly in a conical shape, but to fly in a cylindrical shape. Just because if we fly in a conical shape, the frequency of the 8th figure, and so of the flight, continuously changes, while if we fly in a conical shape, we can fix the frequency, we can fix the length of the trajectory, and so we can fix a frequency which is far from the resonance, just to stay away from the resonances of the platform. So here you can see like the estimation that I used to create this new control system. And yeah, the control system basically works in this way. You can select the flight frequency that you want away from the resonance, and with some subsequent computations related to the geometrical description of the path of the kite, we can define time by time the target points in this angular range, which has to change just because if we maintain the angular points always equal, the flight is conical, while if we change the targets and we restrict the angles, we can fly in this cylindrical shape. So these are the results from the simulation, comparing old method and new method. And as you can see, the displacement both for the x and epsilon direction, which are sway and surge in hydrodynamics terms, the motion is decreased. And so this proves that this simple control system is quite effective. So approaching now the conclusion of my presentation, I just want to give you some messages that I want to underline. So we have some promising results for the tested size of the kite and for wave intensities. Of course, we have to test other wave intensity to be sure that everything is okay. But yeah, the results are promising. And if we deal with offshore, there is this key player, which is the platform resonance, and so frequency becomes quite important in the study. But at the same time, we can see that a simple control approach is effective in allowing the operation of the system. For future developments, the idea is to continue this study for the complete operational cycle, just because I studied only the traction phase, to employ also a multi-body model of the tether, just to go inside the details, also on the frequency of the tether and on the force of the tether. And finally, yeah, to control and optimize the system, also thinking of what we have said today. So that's it. Thank you for your attention.
Thank you. Are there any questions? I have one, and then you, Rishi. Maybe can the mic already be passed? My question was, if you go, can we look again at the equations of motion at the very beginning? No, very beginning, really.
Okay.
I was wondering,
Kite
here, yes, that one. I was wondering, if I look at these, it seems that you have second derivatives of the coordinates, and then you have forces also, but do you consider also the centrifugal acceleration, Coriolis?
Yeah, inside this, like, I also wrote like force for every single variable, but then you can like expand this force, and there are all the components of the motion.
Yes, so this is not only forces but also acceleration terms.
Which are also then comprised.
Clear. Thanks.
Thank you, Sophia. My question was regarding, so you identified resonance as the key player, but then the solution you mentioned was to kind of slightly change the flight path.
Yeah.
But flight path is kind of very critical for the performance of the system. Mm-hmm. But then wouldn't it be also a thing to look from the platform perspective and change the dimensioning of the platform to change the frequency of the platform, and then you avoid resonance in that way instead of changing the flight path?
No, there are clearly like two paths that we can follow. One is the one that I followed now, so this idea for a possible new control system. But yeah, for sure, like the dimensions of the platform, the physics of the platform itself is clearly very important. Changing the dimensions, changing the shape, everything changes, and also the frequencies. So this is like the other part of my work. I'm like trying to observe different dimensions just to see this effect. Yeah,
thank you.
We had coincidentally a similar experience in our wind tunnel when we tested our rigidized soft wing. The whole table was shaking because of the moment and forces inserted into the table in the test section, which is kind of
it's quite
similar. It's not hydrodynamics, but it's just a flexible system. But it's there are many effects that can be studied, definitely.
Yes.
I think now we head over to the coffee break, which is outside, and we, the ones who want to continue in this track, we reconvene then in, I'd say, 20 minutes. We need to catch up a little bit of time. Thank you.